Sawadee ka, architects and civil engineers of the future. Welcome back to your online class in Strength of Materials or Mechanics of Deformable Bodies. I am Daryl J. Amblebeen, your lecturer. In this video, I will discuss Simple Stress Part 2. Specifically, we will solve sample problems in stresses on inclined planes and bearing stress. I assume that you already had an initial read of the concepts of the lesson posted in our previous meeting. Are you ready for it? Let the games begin. Let's have a rundown of the concept of stresses on inclined planes. Stresses on inclined planes occur when the cross-sectional area being considered is neither along the horizontal nor along the vertical, but rather it is inclined to an angle theta, just like what's shown in figure A. Plane AA is inclined to an angle theta with the horizontal. It is under the tensile load P. We have a horizontal cross-sectional area denoted by A. Therefore, this area is A. We draw a vertical line here and a solid line along plane AA. What do you see in the figure? That's right. You see a right triangle. How do we compute for the area of inclined plane AA? Since we're given a right triangle, we're going to use trigonometric function. SOHCAHTOA, sine, cosine, tangent. But which among the three are we going to use? To help you decide, if we have an angle theta in this right triangle, the horizontal area A is the adjacent side, and the inclined plane is the hypotenuse. There goes your clue. Adjacent, hypotenuse. What trigonometric function are we going to use? That's correct. We're going to use cosine function. Cosine theta is equal to adjacent over hypotenuse. Cosine theta is equal to A over the inclined plane. The area of the inclined plane is therefore equal to the horizontal area A over cosine theta. In the figure B, the free body diagram of the inclined plane AA is shown. The vertical tensile load P has a component that is perpendicular to the inclined plane and parallel to the inclined plane. If the inclined plane has an angle theta with the horizontal, the perpendicular force to that inclined plane has an angle theta with the vertical. Just like we've learned in statics, if we have perpendicular lines, mababaliktad yung angle theta. Kapag sa inclined plane, yung theta ay nakakabit sa horizontal, yung perpendicular force or line sa kanya ay may theta na nakakabit sa vertical. So therefore, this is vertical tensile load P, and this is theta with the vertical. This perpendicular force is equal to P cosine theta. Kung saan nakakabit si theta, siya ang magko-cosine. That's why this is P cosine theta, the normal or perpendicular force, and this is equal to P sine theta, the shear or parallel force to the inclined plane. On the third figure, figure C, the normal stress and shear stress on the inclined plane is shown. We have normal stress denoted by sigma, which is perpendicular or normal to the inclined plane. We have the shear stress denoted by tau, which is parallel to the inclined plane. The next question is, how do we get the normal stress and shear stress on the inclined plane? To get the normal stress on the inclined plane, we have the normal stress formula, which is equal to sigma equal to P over A, wherein P is the normal load and A is the cross-sectional area being considered. Sigma is equal to P cosine theta, the normal load on the inclined plane, over A over cosine theta, which is the area of the inclined plane. Simplifying further, we have sigma equal to P over E times cosine squared theta. This is the formula for the normal stress on the inclined plane. Next, we get the shear stress on the inclined plane. The shear stress formula is tau is equal to V over A, wherein V is the shearing force, A is the cross-sectional area being considered. We have tau is equal to P sine theta, which is the parallel or shear force on the inclined plane, A over cosine theta as the area of the inclined plane. Simplifying, we have tau is equal to P over A sine theta cosine theta. But we have a double angle identity, which is sine 2 theta is equal to 2 sine theta cosine theta. What do you observe? Sine theta cosine theta. Sine theta cosine theta. If we divide both sides by 2, we cancel 2 on the right side of the equation, we get the value of sine theta cosine theta, which is equal to sine 2 theta divided by 2. Simplifying this further, we get tau equal to P sine 2 theta over 2A. This is the shear stress on the inclined plane. You do note, however, that we can only use these formulas if the inclined plane is inclined with an angle theta to the horizontal. Again, I repeat, these formulas are only applicable if the plane is inclined to an angle theta with the horizontal. You do note that from the equations on the left, if theta is equal to 0 degree, we get sigma max equal to P over A. Sigma max is the maximum normal stress. It means that when we substitute theta from this formula with 0 degree, we get the maximum normal stress equal to P over A. So that is the maximum normal stress. How did we get 0 degree as our angle. We derive that from maxima in your differential calculus. Also, at theta equal to 0 degree, the equivalent shear stress is equal to 0. Tau is equal to 0 when you substitute theta with 0 degree. Second, at theta equal to 45 degrees, we get tau max equal to P over 2A, or the maximum shear stress. When we substitute 45 degrees in this theta, we get the maximum shear stress. Again, how did we get the angle 45 degrees? Same answer as before. We got 45 degrees from maxima in differential calculus, which I'm no longer going to show. Also, at theta equal to 45 degrees, the equivalent normal stress from this formula is equal to P over 2A, just the same. Let's have an example. The tensile member, 50 millimeters by 75 millimeters in cross-section, is subjected to a load P equal to 200 kilonewtons. The inclined plane makes an angle of 15 degrees with the x-axis. A. What is the tensile stress at the inclined section? B. What is the shear stress at the inclined plane? C. What is the maximum tensile stress at the inclined section? D. What is the maximum shear stress at the inclined plane? Shown on the right is the figure of the tensile member, which has a cross-section of 50 mm by 75 mm. It is subjected to a tensile load of 200 kilonewtons. We are to find out the stresses on the inclined plane AA, which has an inclination of 15 degrees with the x-axis or with the horizontal. Question: can we use the formulas we derived a while ago? That's right. We can use the formulas we derived a while ago because the angle of inclination is with the horizontal or with the x-axis. So let's proceed with the solution. In letter A, we are to find out the tensile stress at the inclined section. Tensile stress is normal stress, and the normal stress at the inclined section is sigma equal to P over A cosine squared theta. We simply substitute our values. For P, that is 200 times 10 raised to 3 newtons. We converted kilonewtons into newtons by simply multiplying 1000, because in 1 kilonewton, there is 1000 newtons. Our A is simply 50 by 75. This is in square millimeters. And our theta is 15 degrees. Bring out your calculators and compute for the tensile stress. The tensile stress you should get must be equal to 49.76 megapascals. In letter B, we are to find out the shear stress at the inclined plane. The shear stress at the inclined plane is equal to tau is equal to P over 2A sine 2 theta. Again, we simply substitute our given values. Tau is equal to, our P is still 200 times 10 raised to 3 newtons. Our A is 50 by 75 square millimeters. And our theta is 15 degrees. Using your calculators, you should get the shear stress equal to 13.33 megapascals. In letter C, we are to find out the maximum tensile stress at the inclined section. For what angle is the tensile stress maximum? For maximum tensile stress, the angle should be 0 degree, so that sigma max is equal to P over A. We simply substitute our given values. Our P is 200 times 10 raised to 3. Our A is 50 by 75. Our maximum tensile stress is equal to 53.33 megapascals. In letter D, we are to get the maximum shear stress at the inclined plane. For what angle is the shear stress maximum? For maximum shear stress, the angle is equal to 45 degrees. That is, tau max now is equal to P over 2A. Substituting the given values, we have our P is 200 times 10 raised to 3 newtons, and our A is 50 by 75 square millimeters. Therefore, the maximum shear stress at the inclined plane is equal to 26.67 megapascals. Bearing stress. Bearing stress is the contact pressure between two separate bodies or two different materials. It is also a normal stress, but it differs from compressive stress as it is an internal stress caused by compressive forces. Shown in the figure is an example of bearing stress. In figure A, that is a rivet in a lap joint. The two bodies or two materials creating bearing stress or contact pressure or internal stress, if you will, are the lap joint and the rivet. In figure B, it is shown that the bearing stress is not constant. And in figure C, however, the bearing stress caused by the bearing force PB is assumed to be uniform on the projected area, TD. This is the projected area, which is equal to thickness of the plate times the diameter of the rivet. What is the formula for bearing stress? As I've said, bearing stress is a normal stress. Bearing stress, denoted by sigma B, is equal to PB over AB, wherein PB is the bearing force, AB is the bearing area, or the area resisting the bearing force. That is equal to PB over our projected area is simply equal to TD. So that is why we have TD on the denominator. Let's have an example. Assume that a 20 millimeter diameter rivet joins the plates that are each 110 millimeters wide. The allowable stresses are 120 megapascals for bearing in the plate material and 60 megapascals for shearing of rivet. Determine A, the minimum thickness of each plate. B, the largest average tensile stress in the plates. On the right is the figure for the problem. We have two plates that are each 110 millimeters wide, being joined together by a 20 millimeter diameter rivet. The plates have a thickness of T, which is what is asked in letter A. They are subjected to a tensile load P, which then causes bearing stress between the plates and the rivet, and also shearing in the rivet. Let's proceed with the solution. In letter A, we are asked the thickness of each plate. We can get that from the formula for bearing stress, which is equal to PB over TD. Do we have PB? PB in this problem is also the tensile load P. But do we have that given in the problem? No. Do we have thickness? Also, we don't have thickness. That's what is asked in letter A. Do we have diameter of the rivet? Yes, we do. That is 20 mm. How many unknowns? There are 2 unknowns. So we cannot immediately use the formula for bearing stress. Rather, let's make use of the shearing stress. And the formula is tau is equal to V over A, wherein the shearing force V is also the tensile load P. And our area to consider for shearing stress is the area of the rivet. This is the shearing area. And that is the area of the rivet, the area of a circle. So in letter A, let's first consider shearing stress equal to tau is equal to P, our shear force, over the area of the rivet, which is a circle, pi fourths d squared. Let's substitute our values. Tau is 60 megapascals, and it is equal to P all over pi fourths 20 squared. 20 is the diameter of the rivet. Cross multiplying this two, we should get the value of P equal to 6,000 pi newtons. Now we proceed with the formula for bearing stress. That is PB over AB. Our PB is also equal to the tensile load P. And our sigma B, or the bearing stress, is 120 megapascals. We leave T as it is unknown, and our D is 20 millimeters, the diameter of the rivet. Cross multiplying T with 120, T goes up, 120 goes down, so that T is equal to 6,000 pi all over 120 times 20. T is equal to 7.85 millimeters. Say T is equal to 8 millimeters. We round up to the nearest whole number. Why? As I mentioned before, the bigger the resisting area, the safer. The thicker the plate which resists stress, the safer. That's why we round up. For letter B, we are to get the largest average tensile stress in the plates. Tensile stress, normal stress. Our P is equal to 6,000 pi newtons, the tensile load P. But what is the area we need to consider? The area we need to consider is the cross-sectional area of the plate. Let's try to draw that. The plate is 110 millimeters wide and has a thickness T. And we also have the rivet, which has a diameter d. Now, the area here we can consider may be T times 110. But we can also have an area that is T times 110 minus the area of the rivet, which is D times T. So we substitute our values. Our P is 6,000 pi newtons. And as I've mentioned, what if our area is the area, cross-sectional area of the plate, which is 110 times T, thickness is 8, minus the area of the rivet, which is T times D. That is 20 mm times 8 mm. We get 26.18 megapascals. The first scenario I've mentioned is, what if the area is just T times 110? You will get a tensile stress smaller than 26.18 megapascals. So therefore, the largest average tensile stress in the plates is 26.18 megapascals. A steel pipe column is supported on a circular steel base plate and a concrete pedestal. It is given that the actual load is 800 kilonewtons, the column outside diameter is 260 millimeters, the allowable compressive stress is 55 megapascals, the allowable bearing stress on the pedestal is 10 megapascals. A. What is the minimum required thickness of the column based on the allowable compressive stress? B. What is the minimum required diameter of the base plate? This is the figure of the problem. The problem is a combination of compressive stress and bearing stress. The steel pipe column is hollow. Ibig sabihin, butas. Butas ang steel pipe column. Let's proceed with our solution. In letter A, we are to find out the minimum required thickness of the column based on the allowable compressive stress. Compressive stress, normal stress, is equal to sigma is equal to P over A. Further, sigma is equal to P over, since we have a hollow cross-sectional area, the area is equal to area of the big circle minus area of the small circle, which is equal to pi fourths quantity big D squared minus small d squared. Substituting our given values, our compressive stress is 55 megapascals, our P is 800 kilonewtons, our big D is 260 millimeters, and our small d is unknown. So we'll leave small d as it is. So we have 55 equal to 800 times 10 raised to 3. We converted 800 kilonewtons into newtons, all over pi fourths quantity 260 squared minus small d squared. Our interest is small d, so we cross multiply what's inside the parenthesis by 55. 55 goes down, what's inside the parenthesis go up. So we have this result. D squared should become positive by transferring it to the right. And this one, we transfer to the left. So that we have this squared equal to 260 squared minus this value. Getting the value of d squared in your calculators, that is equal to 49,080.15208. Getting the square root of the both sides, we get small d, or the inside diameter, equal to 221.54 millimeters. Is this our final answer? No, because what is asked is the thickness. How do we get the thickness if we have the inside diameter and the outside diameter? How? That is simply the outside diameter is equal to the inside diameter plus twice the thickness. Did you get that, class? I hope you did. So this is the inside diameter, and this is thickness. We have thickness, we have thickness, we have the inside diameter. That is why, again, outside diameter is equal to inside diameter plus twice the thickness, as shown in this illustration. Substituting our values, we have 260 as the outside diameter, 221.54 as the inside diameter plus 2t. Solving for t, we get t equal to 19.23 millimeters. Say, t is equal to what? Round up to the nearest whole number. Say t is equal to 20 millimeters. The thicker, the better. Mas makapal, mas safe. In letter B, we are asked the minimum required diameter of the base plate. From the formula of the bearing stress, sigma B is equal to PB over AB, the bearing force over the bearing area. And that is equal to, bearing stress is equal to bearing force over, in this case, the bearing area is not thickness times diameter, but rather it is simply the area of the base plate. Why pi fourths d squared? Because the base plate is circular, so that should be the area of a circle. Substituting our values, our bearing area is 10 megapascals. Our bearing force is 800,000 newtons. And we leave the diameter of the base plate as small d squared. We solve for small d by cross-multiplying d squared with 10. 10 goes down, d squared goes up. So d squared is equal to 800,000 over pi fourths times 10. D squared from your calculators is equal to 101,859.1636. Getting the square root of both sides, we get D equal to 319.15 millimeters. Say, D is equal to 320 millimeters. Round up to the nearest whole number, because the larger the cross-sectional area, the better. So that is our final answer. If you have questions about this lecture, You can always send a personal message in my messenger, or you can post your questions in our LMS forum. Thank you for your time. Kap kun ka. Let me end this presentation with a quote from Maya Angelou. Do the best you can until you know better. Then when you know better, do better. This is Daryl J. Amblebean, your lecturer. Until next time.